Welcome back again, everyone. Let's continue on in our discussion of carboxylic acids and carboxylic acid derivatives, which again are central, or I should say have central importance in chemical synthesis, organic synthesis, and all of the many other fields that organic synthesis touches. We ended last time talking about the acidity of carboxylic acids and why carboxylic acids are acidic. Let's refresh our memory on ways of making carboxylic acids. We already know some of them. In part A of 10.7, we're reminded that you can take either a primary alcohol or an aldehyde and treat it with some stupidly strong oxidizing agent, generally involving a very high valent transition metal, though there's also some silver salts that will do this for us as well. But potassium permanganate with its manganese in the +7 oxidation state, or chromic acid where it's chromium +6, these are amongst the strongest oxidizing agents known to man. And both will oxidize either a primary alcohol or an aldehyde to the corresponding carboxylic acid. And we covered that in earlier chapters. Another way of making carboxylic acids is by hydrolyzing nitriles. Now, hydrolysis comes from two, I believe, Greek words that mean hydro is water and lysis is loosen. So we are loosening by water. And so all hydrolysis reactions involve loosening by water. That would include, by the way, the hydrolysis and saponification of esters, which we talked about earlier. We'll have more to say about that also later in this video. But those are also hydrolysis reactions. And so we are entirely literally loosening that triple bond that holds the carbon to the nitrogen in the nitrile functional group. And the organic product is a carboxylic acid, and we also will get a molecule of ammonia, or technically, I suppose you will get an ammonium ion, NH4+, once you acidify. This can be done by directly heating the nitrile in aqueous acid, or you can also do the hydrolysis, in this case, under alkaline conditions. And that's pretty common for hydrolyses. But once you treat the nitrile with aqueous base, and that could be sodium hydroxide or potassium hydroxide or anything similar, and yes, often that will be heated also. My experience is it's not as necessary to heat it strongly with aqueous base, but you might heat it. It might tell you that it's heated. But once the reaction is done, we will need to neutralize the base and then acidify the solution, because what you actually get at first is the conjugate base of the carboxylic acid, or in this case, RCH2CO2-. And we can't isolate ions. We want to isolate neutral compounds. So we need to add acid, first to neutralize the base, and then to put the proton back on the carboxylic acid and allow us to isolate our neutral compound. So that's another way to do it. That's in part D of this section. And you won't bother. You're not going to be responsible for parts B and C. But the reason I mention this is we already know in principle how to make nitriles. They're pretty easily made by an SN2 reaction. So we covered that in chapter 6. So I've referenced that in your class notes. But we said that you can take an alkyl halide, preferably primary. Secondary might work, tertiary not so much. But in any case, we do an SN2 reaction with our alkyl halide using the cyanide ion. And that then does an SN2 reaction. That's all in one step. And yes, it really does make that sound, at least if you listen carefully enough. And so you will then wind up with the not the corresponding nitrile. The nitrile will have one more carbon than what we started with. And also you get inorganic side products. But the major organic product will, of course, be this nitrile. So what this means is we now know a two-step method to make a carboxylic acid from an alkyl halide. So a lot of this, I suppose the hydrolysis part is new to some extent, though we've seen some hydrolyses before. But most of this is review from earlier chapters. So These are amongst the better known ways to make carboxylic acids. Now, before we get into other reactions, as I said in the previous video, I really want to give you guys some kind of idea as to just how reactive are the different carboxylic acid derivatives relative to each other. And so I didn't see anything quite like this in your book stated in this way. Like I said, they make this point in, I think, section 21 of chapter 10. But I really wanted to put it all in one table for you, all organized in one picture, so to speak. And as we said before, carboxylic acids are actually the least reactive of these towards nucleophilic acyl substitution, towards nucleophiles attacking that partially positively charged carbonyl carbon. And we're assuming always, as much as possible, other things are equal. So this is another other things being equal type of comparison. So no radical changes to R or anything like that. Amides are a little bit more reactive than carboxylic acids. I'm here leaving these bonds to nitrogen unspecified. They can be either to alkyls or to hydrogens. So this can be any kind of amide, really, but amides are a little bit more reactive than carboxylic acids. Esters, a little bit more reactive still. Then comes thioesters. And I don't know that we're going to be really dealing with thioesters. I only mention thioesters because you'll run into them in your biology classes. Thioesters are pretty common intermediates in biochemical pathways, such as our old friend acetyl coenzyme A. That's a thioester. After that, you get to acid anhydride, so it's an oxygen with two of these acyl groups on it. And then acid chlorides are only a little bit more reactive than acid anhydrides, but I would have to say they edge them out. And yes, there are other acid halides too, but I would estimate, at a conservative estimate, 99% of the time, if not even more, we'll be using an acid chloride in synthesis because there are so many more of them commercially available. Acid chlorides are, as reactive as they are, they're a good deal more stable than acid bromides, let us say, and other acid halides. So generally, you'll be looking at acid chlorides. So should you memorize this order? Well, I think it might do you some good. If you want to put the thioester thing aside, just so that's somewhere in the back of your head for when you go on to more biochemistry or biology material, upper level material there. Just so you're aware that they're actually more reactive than regular carboxylate esters. I think that will be a useful thing for you to bear in mind for those classes. But basically, if you would just remember that carboxylic acids are the least reactive, then amides, then esters, and then anhydrides and acid chlorides are almost the same in reactivity, but I really would need to say, in fairness, acid chlorides do edge out acid anhydrides, other things being equal, assuming the R groups are the same. So that, I think, is going to be helpful information as we approach some of these reactions. And so now that we're getting on to these different derivatives, let's talk about those reactions. Only since it's mentioned in your book, I did want to point out that esters can be cyclic. And as you can imagine, the most stable of these compounds are the 5- and 6-membered rings. Cyclic esters are known as lactones. And so I just wanted you to be aware that they exist. Making lactones is very, very similar to making other esters, except it's all done within the same molecule. So they're not really anything different. I don't want you to think of these as being a different thing than acyclic esters, but it just so happens that cyclic esters are called lactones. Good. So we've already said much about esters in general. They can be considered the alkoxy derivative of carboxylic acids, and we make them by condensing an alcohol with a carboxylic acid. And that reaction is known as Fischer Esterification. And again, I do not expect you to learn the full mechanism. It's quite steppy, but I would like to lead you through the reaction, and I would like for you to understand all the steps that it takes and why, and understand what the intermediates will typically look like. I'm just using benzoic acid and ethanol just as an example. I could have used any carboxylic acid and any alcohol. Though I will mention that when we make esters in real life, probably 97+% of the time, the alcohol used will be either ethanol or methanol. So it's usually a small alcohol. And the acid catalyst that we use, it does require an acid catalyst. You could use some sulfuric acid or a little bit of phosphoric acid. There are others. You could use p-toluene sulfonic acid if you're in that kind of mood, but it's just a little speck of some strong acid. And so the first step in the reaction involves protonation of that carbonyl oxygen atom. We've seen that before. That's real typical for reactions in acidic medium, and we can see that we're in acidic medium. We're given that there's an acid catalyst. I do want you to notice very clearly right up front, though, what is not present in this mixture. What is not mentioned is water. And indeed, we're going to be excluding water in this reaction mixture. So if I wanted to do this, I would take benzoic acid, I would dissolve it in a whole bunch of ethanol, I would add a few drops of sulfuric acid, I would attach a reflux condenser and let it cook for a while. I would go to lunch or whatever it is I do. These reactions generally don't take more than a few hours. And then I would come back and expect to have a very good yield of ethyl benzoate floating around in solution, which we can then isolate. So, but it's under acidic conditions, so we protonate our carbonyl oxygen as before. Now we're ready for our nucleophile, ethanol, to attack our carbonyl carbon. And then we are going to have some proton transfer steps. This is very typical for reactions in acidic medium, because we want to set up the reaction for loss of a water molecule. We saw something actually very similar in the conversion of let's see, of a ketone araldehyde to an acetal. And actually, that was in chapter 9. And actually, there's a lot of similarities between making acetals and making esters. I would say functionally or in terms of setup, they would be done very similarly. So just as in chapter 9, we need to get our proton off of this oxygen, and then we need to get a proton onto one of these two OH groups. And it doesn't matter which, those two OH groups are the same. So this can be mediated by an ethanol molecule, can act as our base, and pull that proton off. Remember, alcohols are amphoteric, as we pointed out in chapter 9. And so then you get this neutral intermediate, and then a molecule of the conjugate acid of ethanol, which you're going to have some of, that will now put the proton on one of these OH groups so that we now can have neutral water leave as the leaving group. And so water will then leave and will generate what is actually just our protonated ester. And so all we need now is for an ethanol molecule to pull this proton off and give us our neutral molecule that we can isolate. All of these steps are reversible, I would say, except the loss of water. That's irreversible. Why? Because we do generate a water molecule, but that's now going to drown in this ocean of, in this case, ethanol, whatever our alcohol is. Again, I think we had a rather similar thing going on when making an acetal. So the effect of diluting this little bit of water throughout thousands of mole equivalents of the alcohol, it's as if we removed the water from solution. Now, there are ways of doing that also. There's special glassware that we can use that will do that for us. There's drying agents that we can use that will soak up the water and also pull it out of solution. But even if we don't resort to those methods, it's as if we've removed the water from solution. So all of these steps are reversible, save for that one, but removing the water from the solution, remember that's removing one of the products, and Le Chatelier's principle tells us that we can drive an equilibrium forward by removing one of the products. And so that's what we do. So the equilibrium lies toward formation of the ester. One thing that's very important to understand that I wish they'd emphasized more is you need to use acidic conditions to form an ester. It can't be done under alkaline conditions. And I think that if you consider it for a moment, you'll see why. If we were to dissolve our carboxylic acid, whatever it might be, in some alcohol and now add base like hydroxide, well, all the base will do is just pull the proton off the carboxylic acid and game over, and it's done. There's no way that this can react further with any nucleophiles. There's already a full -1 charge on that species. So it's done. It's not going anywhere. So that's why you need to use acidic conditions. Alkaline conditions will not work for Fischer esterification. Now, we made the point that Fischer esterification is reversible, and you can drive the equilibrium in the other direction by using not a large excess of alcohol, but a large excess of water. So if you were to add the ethyl benzoate to just aqueous acid, dilute aqueous acid, generally these do require heat as well, you will drive the reaction in the reverse direction. It's the same exact steps, you just rewind it. It's just exactly backwards. So the first step would be to protonate the carbonyl oxygen, then a water molecule will add, which now there's plenty of water around, and then we'll do again some proton transfers. We first remove a proton from this oxygen, and then we add it to this oxygen so that we can now lose a molecule of the alcohol, in this case ethanol, as a leaving group. And then we do that, we lose the alcohol, which now is drowning in this sea of water, essentially. And so you get your protonated carboxylic acid, and then we pull that proton off, and finally we get our neutral carboxylic acid. But we also know from chapter 15 that you can hydrolyze esters in base as well. It's called saponification also. And the reaction in base looks somewhat different. One thing I've noticed about reactions in basic solution is that they tend to be simpler. There's fewer steps involved. And I think you'll see that that's the case. Since we're in basic solution, now we don't have to worry about forming a minus charge in this oxygen. Because just as we didn't want to form any strongly basic anions in acidic solution, now this is turned on its head. Now we're in alkaline solution. So now it's totally fine to form strongly basic anions. Well, we want to avoid forming our cations. We don't want to see any carbocations, no oxygens with a plus charge, nothing like that. The only cations that you can conceive of as being in alkaline solution are metal cations, Na+, K+, Ca2+, things like that. And they're not going to do anything anyway. They're just going to be spectator ions. So what that means, remember NaOH means Na plus OH minus, so the hydroxide ion is our nucleophile. In alkaline medium, it's just bombs away. Our hydroxide ion attacks the ester. We get this intermediate that leaves an oxygen with a minus charge, which is just fine in alkaline solution. Acidic solution, no. We would want to avoid showing anything like that happening in an acidic solution. This now loses a methoxide ion as a leaving group and forms a carboxylic acid molecule. And if we cared to show it, the methoxide ion would very quickly deprotonate a molecule of water, which is around here in plenty, and you would get your alcohol molecule that will now be drowning in an ocean of water. But this is something subtle but important to understand. We've just generated a carboxylic acid molecule in alkaline solution. And so remember what this means when we draw steps, step 1, step 2. It means we're going to add our aqueous base to this. And again, I just used methyl hexanoate as an example. And we're going to wait until everything's done reacting. And then we'll acidify. We need to do that, otherwise we won't get a complete reaction. We'll only get some of the molecules to react. We won't get a clean reaction. So since we formed this carboxylic acid in alkaline medium, that will immediately react with the hydroxide ion, which is an excess. You can't stop that from happening. And so it's going to be this carboxylate ion, the conjugate base of the carboxylic acid, that's going to be floating around quite happily in the solution until we acidify. So you don't get to say, oh, there's my product, I can stop now. No, you need to consider the nature of the solution that this molecule was just formed in. If we were in acidic solution, we'd be done. That's not going to react any further. But an alkaline solution, you can't stop the carboxylic acid from getting deprotonated. So now, once everything is done getting saponified and everything's converted to methanol and the hexanoate ion, then we add dilute aqueous acid. The first action of the acid will be to neutralize all of the sodium hydroxide that's left, and then it will start putting the protons in the carboxylate and will isolate our free carboxylic acid. So it's an interesting way to focus on the differences and similarities of the two hydrolysis reactions in acidic medium and alkaline medium. So I think that will be worthwhile for you guys to ponder. Other than that, I think that's a good place to end. Let's leave the last part of the chapter for one last video. So until then, have a good day.